name is Anushka Rai, and I welcome you all to this talk today on behalf of the Naresh Vashas Center for Tinkering and Innovation, which we also call in short NVCTI, IIT ISM Dhanbad. I hope everyone had a great Christmas yesterday. We are in the middle of the festive season, and yet we're all here gathered today because we all share this enthusiasm for learning, and it's great to see everybody here. I'm sure everyone is excited about today's session. So before we begin, just a few things. First of all, it's a humble request to all the attendees to keep themselves muted during this entire event so that there is no background noises or disturbances. Also, I would like to thank our professors, Professor Pankaj Mishra sir, who is the Associate Dean and Head of Center of NVCTI, and Professor Ajit Kumar sir, who is the coordinator of the Institute event, without whom this event would not have been possible. So thank you so much. They're not here today. They couldn't be part of the session, but we still thank them for helping organize all of it and bring it to you. So as we finally coming up to the session for today, as we all know, this session is related to the topic of robotics and AI. How many times have we not heard about AI? AI is being called the new electricity of our generation because it's bringing in these massive changes in the industry and hence as a result in the lives of people. And it's very interesting to see how AI relates to robotics, because that is how the first imaginations of AI were, robots using artificial intelligence. But what most people don't know is that robotics and AI can be combined in a lot of different ways, apart from the classic robot that looks like a human imagination that we tend to have. So this session is about that. So without further ado, let me welcome our very special guest today, who is going to be taking this session. He is the co-founder of ResumePuppy. He has also worked with companies like Tesla, Lyft, and Nuro. On top of that, he's also the recipient of the Einstein Visa, which is given to extraordinary professionals. So please welcome Mr. Saiman Shetty. Sir, please welcome to the session, and the virtual platform is yours.
Thank you so much, Anushka, and everyone else gathered here today. Such a pleasure to be talking to a lot of folks from this reputed institution. So thanks for having me here as well. Super quick, a little bit about my background. I think it's already mentioned, but started working in industrial robotics that you can see on the bottom right of the screen. Basically robots that go into the manufacturing, packaging, that kind of industry. And then I made my way into a company not that well known back then called Tesla. And that's why I moved to Silicon Valley to help build the two beautiful vehicles that you can see on the top left, which is the Model S and Model X. From then I moved on to Lyft's self-driving group as almost a founding member of the self-driving group at Lyft, and helped deliver this vehicle that you can see here on the bottom left. So self-driving vehicle. And then since then I've moved to another amazing startup called Nuro, which makes delivery robots, which you can see on top right. So this has been my overall journey, mostly in the space of robotics and AI and application in autonomous vehicles, a little bit of manufacturing and stuff like that. But then why is this exciting, right? Like, why is this field of autonomous vehicles specifically interesting? One of the biggest examples I can give you, or some of the biggest examples I can give you, are all the logos that you can see here are invested in some way or the other in self-driving. And given there is so much investment in self-driving and so much motivation to get vehicles to the autonomous mode, all this research is adding up to a lot of opportunity a lot of jobs as well, and a lot of secondary things as well. So what do I mean by secondary things? Now, these are the primary players, right, who are directly invested in bringing self-driving to the masses. Now, if you peel one layer of that onion, you can see that it's not just those companies. There are hundreds, if not thousands, of different industries that are feeding to this self-driving industry that is worth several $100 billion, probably more than $1 trillion now. And what are those companies, right? Like you need compute, you need braking systems, you need data and connectivity, sensing, processing. All of these, a lot of these companies that you can see here are relatively traditional companies like Bosch and Pioneer and Toshiba, but they are delivering new and innovative stuff to the self-driving world. So the message I'm trying to pass through mentioning this is that probably any industry you step into or any field that you are in, be it engineering or finance or any sort of business stuff, even legal, whatever field you are in, there is a space, there is a place for you in AI and self-driving. So and this is how it all adds up, especially also the companies that make tools, right, like MathWorks and Polysync and all of these people. It all adds up to what these main players use. So that's why this whole effort is exciting, and it's getting easier to be part of this, directly or indirectly. Now, what do we actually mean by autonomy or different stages of autonomy? Now, the Society of Automotive Engineers basically defined this as 5-step or 5 levels of automation. So the initial is where you start from is basically level 0, which is no automation at all, completely manual car, doesn't need any explanation there. And the level 1 is basically driver assistance, which is kind of like cruise control, single dimensional automation. Level 2 is partial automation, where the vehicle has automated functions on the acceleration and steering, but the driver must still remain engaged with the driving task. Now, what does that mean? Maybe something like an adaptive cruise control. That's what it means, where your vehicle can probably control like 2-dimensional and maintain a lane and things like that, but still you need to remain engaged. And level 3 is conditional automation. This is where companies like Tesla are at now, or are trying to get to right now, where the technology lies, especially where the software lies, right? So here the driver is a necessity, but is not required to monitor the environment at all times. So it's like there are some corner cases that the vehicle cannot handle, where the autonomy system sort of falls back on the driver, and the driver needs to take control and do some things. And then passing from that stage, you have high automation, where the vehicle is capable of performing all driving functions, right, under certain conditions. The driver has the driver taking control of the vehicle is actually optional in this case. So and this is where the current Tesla vehicles, for example, being made are designed for level 4 autonomy once the software is mature. And why is it level 4 and not level 5? Well, level 5 is where you pretty much take out all driver controls, right? Like you don't have a steering wheel, don't have brakes, you don't have anything, and it's like complete automation without an opportunity for any driver to take control of the vehicle manually. So that's that utopian state of automation that a lot of companies are aiming for, but it is yet to be proven and validated over millions of miles, if not billions of miles, to prove the reliability of it. Now, this is a concept vehicle from Bosch, basically like a level 5 vehicle, because you don't see any driver controls over there. It's basically a cabin which shuttles people around. So this is how a fully level 5 vehicle would look like. Here's another vehicle from a company where a lot of my friends work at, Zoox. And similar thing again. The really interesting thing about this is that and my most favorite part about this is it's designed so smartly that the vehicle is symmetrical around both sides. So both the tires rotate along, basically are capable of turn execution. So whenever the vehicle drops someone off, and if it wants to take off in the other direction, it doesn't really, or if it parks a certain way, and then if it wants to get out, it doesn't really need to reverse, so to speak. It just switches sides. So the brake lights become the headlights become the brake lights, and it's just the vehicle is flipped. So that actually helps out with a lot of like corner cases as well. And it's a cool feature, but I really like that feature about this vehicle. Anyway, so how do self-driving vehicles actually operate? Now, I'm assuming a lot of folks here on this call are from an engineering background. So I'll keep it relatively technical in nature. So just like humans do, the vehicles gather environment conditions from the different sensors that the vehicle is equipped with. It filters and interprets the sensor data, which is basically perception. And then it decides what to do given the scenarios that it's looking at, and then it issues commands to the vehicle actuators and the vehicle controls to basically assert that motion control. Pretty much the same as how humans do, but in a in a much more sort of resolute manner, because the computer is capable of processing data much quicker than humans are. What the computer is not able to do right now is have the power of intuition, have the power of this pattern learning, which AI and ML is basically filling. But overall, there's a lot of different things going on here, which is very similar to how humans drive the vehicle. Now, just an arbitrary drawing here that shows different sensors, sensing modalities. You can see the LiDAR, the video cameras, computer vision, the radar sensors, central computer that collects everything and decides what to do, odometry sensors to complement the GPS so that the accuracy for localization is improved, and ultrasonic sensors for like near field stuff like curb detection, parking assistance, and things like that. And then of course there's the GPS. Now I want you to pay close attention to the different costs of these things, because that's what I'm going to talk about. I'm a huge believer in designing technology that makes sense commercially, right? So there's no point designing probably a $500,000 car if you cannot make the economics work. And the different people are targeting different industries. For example, Tesla wants to make a mass market car that is autonomous, versus a company like Waymo wants to make vehicles that are not sold to customers, but basically kept as a taxi service. So how much flexibility you have in what kind of technology you want to put in both cases is very, very different. And why is it different? Because in a mass market car, there is someone else paying for it, but then if you operate it as a taxi service, you can amortize the cost of the vehicle across the number of rides it will give in its lifetime. And then that's how the economics is a totally different equation there. Now, just a few snapshots here. This is a Tesla vehicle. Tesla is notorious for not having LiDARs at all on vehicles. So basically they were doing vision plus radar, and now they've probably taken off the radar as well. So it's pure vision based autonomy system that Tesla vehicles are equipped with. Anyway, so on the right side, you can see how different cameras around the vehicle are perceiving and labeling the objects that they are seeing, and then recognizing the world around it, just using computer vision. And you can see you can see the legend, so to speak, down about like what means what. This is another video from Uber, actually, where you can see the vehicle is actually planning its path for the next few seconds in front of it. So the green path is, it looks at different agents outside and then sort of plans a path, which then it issues to the control system to basically execute and make the vehicle move along those paths and along that path. What you can see here is a radar point cloud. So basically what a point cloud means is the radar spits out radiation, of course, and then it looks at the reflection, and whatever reflects from the target and comes back, it paints it as a cloud of points. And that's the point cloud that you're looking at. This is basically how a radar perceives the world around the vehicle. This is a LiDAR point cloud. Now you can see that the radar point cloud was much less dense, not that much information that you can solely depend on that to drive. This is a LiDAR point cloud, much more granular and detailed information coming back that you can use to execute your motion. So basically, but they complement each other, and I'll talk about that in one of the future slides. But this is how different sensors are fused so that you can use the best quality of each of them to basically make a decision and move. This is one of the hardest things to do. This is a Waymo vehicle, and it is autonomously executing a negotiated left turn. So in the US, in the traffic light, if there is no left arrow, that's green, and if there's just a solid green, then it is on you to negotiate that left-hand turn with oncoming traffic. And that is a very tricky game because you have to understand the intention of the person who is driving towards you, and then look at their speed, be very cautious, and then execute that turn. And this is what the Waymo vehicle is doing very seamlessly. And this is a really interesting case because a lot is dependent on those non-verbal cues that humans communicate in, right? Like eye contact and things like that. That's how we sort of understand the intention of another driver and then design our actions around it. And over here, you can see the self-driving vehicle basically doing that with a bunch of different parameters that is factoring in. Of course, sensing systems, these are all this is basically a sensor pod of one of the self-driving companies. You can see the cameras over there. You can see the LiDAR. You can see a flat surface between the two cameras or between different cameras, and that's basically a LiDAR probably hidden behind it. Sorry, a radar probably hidden behind it. So that's that surface. And you can also see small jet sprays above the cameras just to clean the cameras if in case of any dust or any bird poop or something like that. And then there's also long range and short range cameras right in front of it to detect like traffic signals, things like that. Some vehicles are also equipped with infrared cameras so that you can detect maybe a human or someone walking across the road, even in low visibility conditions like fog and things like that, rain, things like that. Anyway, so all these sensors, they complement each other. So you can see here how different sensors are used primarily for different specific purposes, but then overall you can also cross use them for different for other purposes as well. So like I said, traffic sign detection, surround view, blind spot detection, park assist, adaptive cruise control. That's a long range radar for adaptive cruise control because you need to see further ahead and adapt your speed to the vehicle in front of you. But overall, this is how different sensors specialize in something, in a unique use case. Now, why the question comes up, why can't you use like all the sensors, have like double, triple redundancy and then be on the way, right, doing things? We cannot do that for multiple reasons. One, to be technical in nature, a lot of these sensors, stuffing a lot of these sensors in the vehicle consume a lot of power and it overwhelms the power system in the vehicle. That's one. But then the even bigger reason, I mean, theoretically, we can overcome the power problem. That's not a big deal. The bigger problem here is the cost and the economics of it, the business side of things. Again, you can't have like 10 lidars and make the car cost $500,000 and then expect to make money on that business, right? So the way we look at this is that different sensing modalities, different sensors have different strong points and different weak points. Now, the cost of a camera is really, really low compared to the cost of the LiDAR, which is super high, and the radar also. Now, the reason the camera is super low is because phones and laptops and all of these, camera image capturing technology has come so much advanced that that we can make cameras for cheap these days. That's not the case with LiDAR, because LiDAR has a lot of moving parts, new technology, so it takes time for the cost to come down on that. And the negative of the camera, for example, I'm just telling you one, but you can look through this chart, this matrix. The negative of the camera is that you cannot use the camera if the camera can't see something, which is like low light or let's say fog or rain, it really can't see things, then the camera fails, right? So that's where you need like lasers, LiDAR, and sound, radar to basically detect the targets and make you understand the world around you. But then there's also noise, electrical noise and signal noise and things like that, range, resolution, weather, velocity tracking, height tracking, distance tracking, classification. You can see the matrix where these sensors have a complementary set of characteristics. Now, after all of the sensing and planning, what is also important is prediction, and this is also a really interesting part of AI that self-driving vehicles use. Now, if you look at the bottom left camera feed, you can see that there's a cyclist, and there's a cyclist on the bike lane, of course, and then there's a trailer parked there, right? And what does the cyclist do? The cyclist veers around the trailer. Now, if you are inside a vehicle driving on that lane and the cyclist is heading towards a trailer parked on their lane, then you would actually predict that the cyclist would veer into your lane just to avoid that trailer. And then so you would be cautious, slow down or speed up, whatever it is, however adventurous you are. You basically do that, right? So a self-driving vehicle should actually predict the behavior of an external agent as well. So in the bigger picture, you can see here that not only the self-driving vehicle is planning its own path, it's also predicting the path of the two cyclists in that red line, and then slowing down, deliberately for them to pass that trailer. So this is a crucial part of avoiding accidents that humans adopt, and this is what we need to teach the self-driving vehicles to do as well. And this applies to this is just one scenario, right? Like there's hundreds of thousands of scenarios that we subconsciously negotiate like this when we are driving, which we really need to find a way to teach self-driving vehicles how to do. Now, how do self-driving vehicles localize themselves, and how do they conduct business, right? How do they really get from A to B and things like that? So there's a base map. There is basically like the Google Maps that we use. There's a base map. We use the base map to try to navigate ourselves somewhere. But a self-driving vehicle, that's not enough. You need a LiDAR and radar, like geometric map, which is basically the entire route mapped using a LiDAR and radar. And it's a visual geometric map, and then a semantic map, which basically constitute a high definition map. And then on top of that, you load like traffic scenarios, weather scenarios, map priors, data driven, basically traffic, all these other things that you can derive from historical data. You just overlap on that, and then it uses these multi-dimensional maps to make decisions on where to go and what to do and things like that. There are some aspects of this that are not scalable and need a better solution, of course. Like you can't expect to create a LiDAR map of every street in the world. You can probably do it in a city, but then the self-driving service you launch will be only good for that city, right? Like, how do you scale to another place? You are stuck at that point. So you need to design technology that can actually self-map, or it can it can operate without such specific maps when it goes to uncharted territories as well. So this is in general how product development happens in any industry, for that matter. That doesn't really apply to self-driving, but it's worth looking at. This, of course, a problem, and then you design a prototype and test that solution out, and then improve it, and then research again and prototype and test. This is the exact same thing that happens in self-driving. It's been going on since the close to a decade, if you count the primitive self-driving stuff, but definitely for more than half a decade now, if you look at all the modern self-driving technology that has come out. Now, self-driving is a very unique niche case of robotics, of course. Like the car is a robot in itself and it drives. Now, robotics is a broader field that also is super, super exciting. Now, for example, this is a tractor that someone took a CCTV camera kind of thing for perception, and then there's like a compute there for decision making, and then all the actuators at the back that it triggers to attain the desired outcome, right? This looks like a regular construction site, except for the fact that these vehicles do not have drivers in them. This is a company that makes fully autonomous construction company as a construction equipment. And think about it, this can run literally 24/7, day and night, doing stuff. And imagine the amount of velocity it will add to the whole construction process, the whole industry in general. You can see a little surfboard kind of thing on the roof. Inside that is a self-driving computer and all the other sort of processing systems. This is, of course, a prototype, and that's why things are a little scrappy here. But then the bigger point is that there is no driver, and it's driving by itself. And then there are like sensors to take care of where it goes and stuff like that. This is another interesting company called Zipline. It's operating out of Africa. What they do is they deliver things like blood and medical equipment, medical supplies and things like that to places without connectivity, road connectivity or anything like that. So what it does is it has a payload bay, and then they load the payload bay with whatever they want, and then they shoot it into the sky. Of course, if they catapult a plane like this that quickly, it attains its lift velocity super quick, and then it flies. And it flies to that location. That location has the hospital or whatever place it is. It has a landing spot, so it parachutes the supply out to them, and then turns back and comes back to base. So you see how they've totally skipped, instead of building roads and incurring all the time and cost of that for especially medical and emergency related stuff, they just took the alternate route, which is the skies, with an autonomous aircraft, which is literally saving lives. Now, how do you need runways for planes and things like that? Of course, you can catapult it into the sky, but how do you actually land it? Planes that have fixed wings cannot really land that easily, right? I'm sure it needs runways and things like that. So here's an ingenious solution. Why not catch it from the sky? So you can't keep buying land everywhere you go and add to your cost, but also it's a logistical nightmare. So that's not going to work, right? But you can actually design a system that basically catches it from the sky. And this one is scalable and repeatable business-wise, because all you need is like a bunch of land, and then you can repeat this. You don't need to care about like wind speed, probably a little bit, but not that big a deal as a precise landing on a runway kind of thing. Of course, there's precision super important in catching a plane from the sky like that. But then what I want you to appreciate here is how they've made business sense out of this, even in every aspect of the solution. And we have all seen this Boston Dynamics robots, which are dancing to the tunes. I really like how they do their marketing as well. Very innovative. But then in general, yeah, this is how the robotics industry, especially self-driving, but in general, the robotics industry is going forward, and that's why you really need to be a part of this, because this is being in the robotics industry now is like being in let's say the internet in early 2000s, or maybe late 1900s, 1990s, and then it's also like being in the semiconductor industry in its infancy back in the 60s and the 70s. That is what robotics and AI is going. Self-driving is that's the phase it is in now, and I can only be excited about everything that has to come from this point. Of course, you can follow me on LinkedIn, and I'll definitely be happy to connect with you there. But let's open this up for Q&A. I want you to ask me some super interesting questions.
Sir. Hello. Sir.
Yeah, go ahead with it.
Sir, what is the use of that steering given in that cars, autonomous cars? Like, can the driver control it at any time?
So
external steering.
Vehicles that are designed to have the driver control them, to give the driver an option to control them, yes, they'll have steerings. Like, just simple example is how Tesla vehicles are built as of today and until today, right? Like, they have steering wheels in them. But then vehicles that are intended for true level 5 autonomy do not have steering, or mostly will not have steering wheels or any sort of control surfaces in them, so that you don't need a person to take over control.
Sir?
Yes, go ahead.
So can I speak?
Yeah, please.
Yes, go ahead.
Sir, you talked about the shipment airplanes lastly, and sir, how the company controls it, about the path it will follow and to the place it will land.
So there's no, I mean, it's very similar to autopilot, or I mean, not autopilot, but like drones, autonomous drones. It is an autonomous drone for that matter. There are waypoints that, there's designated dropping spots, of course, and then there are waypoints to those designated dropping spots that the airplane is instructed to execute, and then it goes there. Of course, it doesn't land, it just parachutes the thing out, makes a turn, comes back, and basically the rope catches the plane. So it knows the precise location of the rope, and then using vision and several different sensing modalities, the rope also catches the plane that way.
So why don't we use drone only for this purpose also?
So the payload capacity of a drone is significantly less than a fixed wing aircraft. I mean, this is similar to a question of why do we need like jet planes and huge runways to transport humans, right? Like, why can't we use drones? Basically, a helicopter is a version of your question. But then a helicopter, there's only so much weight it can lift, and there's only so much distance it can go for just a kind of, and it's like relatively expensive. What you need here is a very cheap solution that is reproducible time and again, and very reliable in a fixed wing, in a drone, or probably like a quadcopter kind of thing. there are a lot of moving parts that can break and things like that. Reliability question, maintenance question comes into play. And on top of that, if it is not able to lift like sufficient payload and doesn't have sufficient range, then it virtually becomes useless in front of a solution like this, especially in a continent like Africa. So that's the main reason here. Does that make sense?
Can that automatic plane counter the fast winds?
Sorry, say that again. I didn't get you.
Can that automatic plane counter the fast winds?
It is, I mean, like any airplane is designed, it has its own thresholds of what kind of crosswinds it can tolerate and things like that. So like, for example, if there's like winds above a certain speed, airplanes don't take off, right? So similarly, it has its own thresholds, or I believe it has its own thresholds that it needs to obey. And it's not traveling like hundreds of or thousands of miles. It's probably going to travel like maybe 50 to 100 miles, something like that, to deliver and come back. So the weather patterns that it, and also the altitude that it flies at is also, I believe, relatively low, so that we can, and the point I'm trying to make is everything is relatively more predictable than a long haul aircraft that you don't know what it might get into along its way.
So that trajectory of the autonomous plane, like how it takes flight, it was swinging. So in what way it flies?
You're asking how it took off?
Yes, sir.
So the overall goal in any fixed wing aircraft is, of course, to have the pressure above the wing to be lower than the pressure below the wing, so that it attains the lift, right? Which counters the gravitational pull of the Earth. That's the general physics behind how any plane takes off, any fixed wing plane takes off. So how do you introduce that pressure difference along, between the two surfaces of the wing? Is by speed, right? And how quickly you can get it to that speed is why planes sort of take off on the runway and things like that. Here, it's basically catapulted into the sky. So it has a huge acceleration in those few meters that it is catapulted. And then once it is in the sky, it is designed in such a way that that catapult is enough to supply sufficient speed or velocity to it. So it generates a reasonable amount of lift that pushes it into the sky.
So, sir, is there any particular angle of release?
There should be. Again, it depends on the design of the wing, and of course, since the catapult is specifically inclined in an angle, you have much more control on the angle of attack that the wing goes through, and then you have much more control over like how to design the wing, because you design the catapult as well, right? So to answer your question, yeah, I mean, there definitely is a certain angle there.
So let's say I'm a manufacturer and I want to achieve level 5 autonomy. So where should I put my money? Like, should I have to research more on lidar and radar, or just improve the current computation algorithms and put more work?
There are different schools of thought on this. The only company that I see that is like super serious, or rather the first company that I saw that's super serious on taking autonomous vehicles to the masses, commercializing it as a consumer product, is Tesla, right? And that's the main reason Tesla is not using LiDAR, because the moment they put a LiDAR on the vehicle, they significantly reduce the reliability of the vehicle based on how LiDAR technology is at this point. And they significantly increase the cost of the vehicle, which makes it unaffordable, which makes it not a commercially viable product, and then it doesn't become a mass market vehicle that people that's where Tesla wants to go. So you should look at things, if you are asking me where you should put your money, you should look at, okay, if you are targeting the consumer market, what kind of price tolerance do these people have? What kind of reliability requirements do these people have? And if you are warrantying that vehicle, how can you build the cost of all warranty coverage into the price of the vehicle? And is that affordable to people? These are all the calculations that you need to do to decide, what kind of technology you need to use.
So another one on on fusing different values of sensors. If there is a situation where different sensors give us different data, so for which one do you give more reliability or priority to make a decision?
That's actually a really interesting question. So this happens a lot of times when you get conflicting data points from different sensors. There's a variety of things you can do, and if nothing works out, there's a couple of other things you can do. So the variety of things, basically, you look at different feeds, right? And you approach it from a very conservative angle, and you see what is the most serious input, right, that you need to worry about. Again, if you have like redundant systems and things like that, and they don't match, then you have a problem, and you need to then, there's a few different ways of failing. There's fail safe and there's fail operational, right? Fail safe is basically your vehicle says, I don't know what's going on. I'm going to be super conservative. I'm going to bring myself to a complete stop, maybe turn the hazard lights on, and that's it, right? I have failed safe. Fail operational is basically, and this can happen, you can adopt fail safe, fail operational, specifically and individually for different types of faults. So for some faults, you can fail safe. For some, you can fail operational, depending on severity and things like that. You might have heard of this field of study called functional safety, which goes into the design of pretty much any consumer product that affects human safety as well. And if you're really interested, you should look into that field more closely. But in general, what happens in fail operational is that, okay, you have some issues with some sensing modalities or something like that, but then you still have sufficient capability to execute your mission successfully, and then call it a fault. So that's when you enter the fail operational mode to finish the mission, and then say, okay, now I need some attention.
Sir, can the passenger vary the speed of the autonomous car?
Depends on, well, you can program it, right? Like it depends on, like if it's a taxi service, do you want if you are operating a self-driving taxi service, do you want your passenger to actually vary the speed? Probably not. But if you're probably selling a commercial vehicle, consumer product, something like that, you probably want to give the customer the authority of setting max speed, things like that, just to make it a little more personalized. All of this is software controlled, so you can do anything you want.
Sir, within the driving only, while driving only, can we change the speed? Like as we usually do.
That's what, if you are building a self-driving vehicle, you can design software that either gives the customer an authority or deprives the customer of that authority. Like for example, Tesla Autopilot lets you set the max speed. But if you call a Waymo taxi, you can't set any speed on a Waymo taxi that is fully autonomous, because that's none of your business, right? Like that's the taxi's business.
Hello. So, sir, apart from the controls and all, like the power is a major part of any vehicle system or something. So, according to the current technologies, what are the industries are planning? Like currently, we are using batteries, and also how much efficient they are, and what are the other power sources are the industry like researching and all?
So you're talking about the energy side, right? So in general, autonomy and energy or what the car runs on, or what the vehicle runs on, are two sufficiently disjoint problems. You can make a gasoline or petrol vehicle autonomous, and you can make an electric vehicle also autonomous, no problem at all. And that's being done as well, right? But in general, in my experience, I've seen, and many people would agree, that an electric vehicle has much more controllability than any fossil fuel based vehicle, mainly because it's instant torque. You can independently vary speed, things like that, across the different tires, better traction, stuff like that, which you either cannot do in a gasoline vehicle, or it is very prohibitively expensive to do in a gasoline vehicle. So to answer your question, people are pursuing self-driving in like electric vehicles, gasoline vehicles, all sorts of vehicles.
Sir, in the venture to reduce cost, how far do you go to reduce the number of sensors you're giving? So just in case the sensor starts to fail, how are you going to know the sensor starts to fail?
There are different. So I really like this question actually, because there are different ways to approach it. There's redundancy, of course. And then there's also this question about like, hey, if I have two sensors of the same type, and one is saying X and the other one is saying Y, who do I trust, right? There's that. But then there's also multiple other sensors that you can compare the inputs with, multiple other sensing modalities that you can compare inputs with, and you can either do a majority vote kind of thing, or you can, if a sensor is clearly failing, you know that a sensor is off, your camera is off or something like that based on diagnostics, then you can reject the input, because you know that it is like, probably that there's like bird poop, or probably that it had suffered, let's say, like an electromagnetic spike or something like that, which corrupted the signal coming from it, whatever it is. You can rely on such diagnostics to basically decide which one might be faulty. But then in the absence of all those diagnostics, that's when the problem becomes much more interesting. If all your diagnostics are telling that, hey, all my sensors are good, and still it doesn't match, then you open a whole big field of functional safety again, right? Like, what do you do? This is all a game of statistics at that point, where there are a few different ways, a couple of which I mentioned to take care of that issue.
So, and another question, another question. In case like there's a decision to be made, like we humans have a sense of morality, right? So who takes priority, the passenger or say a pedestrian, in case there's an unavoidable crash?
Again, you're asking a question that is very dependent on the person that is designing the self-driving vehicle, right? Like, for example, this is not something that this is something that humans program or need to program into the vehicles. Different schools of thought suggest different things. Like, for example, if it comes to a point, like, for example, Nuro, right? Nuro does not carry passengers, which gives it a significant advantage of development over all these other self-driving vehicles, because instead of putting airbags inside, put airbags outside to protect pedestrians, things like that. So your use case becomes much more simpler, not simpler, but much more interesting, and helps you lean a lot towards not hurting someone outside the vehicle. There are other companies, of course, a lot of other companies that do taxi services with passengers outside, passengers inside, pedestrians outside, passengers inside, things like that. At that point, it becomes, I'm thinking very soon there will be a legal framework that requires a certain minimum level of prioritization on these things, because after a certain point, it just becomes bizarre where people can program anything. But then in general, if you own a self-driving vehicle as of today, you are responsible to not hurt someone. Like if the vehicle hurts someone, then you have hurt someone. That's how the law treats, especially at least in most parts of the world. And that you can either be a person, or in many cases it can be a company, and they are liable for it.
Thank you, sir.
So do we came to know that our sensors are not working?
Sorry, say that again.
So do we came to know that our sensors are not working?
Yeah, that's what the diagnostics are for.
Sir, do those sensors try to fix them on their own cells also, means that device?
There are, so based on what you read from your diagnostic, there's different types of modes you can put the sensor in. If you want the sensor to like reboot, then you can probably issue a command for it to reboot if it's safe to do so. If you want, let's say, if the camera is clogged or a LiDAR is clogged, cannot see stuff and things like that. If you have like a flush or a cleaning and clearing system, whatever it is, you can activate those systems as well. So there's a fair bit of things you can do to self, repair the sensor, at least to complete the mission, or at least to get the vehicle back to the safe mode of operation that it was in.
So that command is given by us. I'm asking that those sensors will do this on their own.
So that command can either be given by, there can be probably a, you can put it anywhere, right? Like for example, you can have it at the endpoint, sort of like an edge compute, not really, but like an edge compute where you have a compute on the sensor that detects these things and automatically triggers it. Or you can have it in the electronic control unit, where that controls different, the sensor and its cleaning system, or things like that. And I'm just taking an example of cleaning system here. Or it can be in the main compute, or it can basically be like the vehicle issues, which is a relatively inefficient way to do it, but the vehicle issues a signal back to teleops, and then some human back in teleops issues the command and clears the sensor. My point here is this all of this comes in vehicle architecture, right? Or basically architecture of this product, where you decide, if you are the engineer, if you are the chief engineer, you decide which is the best point to do it.
Thank you so much, sir.
Can I ask just one more question?
Sorry, but we are at the end of our time here.
Anushka, just a second. Good evening, sir. Good morning, sir. For you, it's evening there. So I have one question to like sum up everyone's doubt, I guess, from India especially. Like, considering the level of technology sophistication at present we are having, and the rushness and the traffic of India, especially of India, what do you think is the status at present that these autonomous cars should be launched or can be launched and will be successful in the Indian traffic condition?
So there are, if you look at it from a business side, just keeping the technology on a shelf at this point, I think there is immense potential. And just compare it to how like Uber and Ola and all these other people, players are doing in India. I think there's immense business potential here. Now, coming to the technology part, where self-driving vehicles are flying or really gathering a huge pace right now are in countries where the infrastructure is relatively repeatable across markets in that country. What does that mean? In the US, for example, you go to the highway code is relatively similar across the country. The signs are relatively the same. You go to a city in California, you go to a city in Utah, you go to a city in New York. A lot of things are very predictable, right? Because everything is like per a certain code, which becomes a little hard when it comes to a lot of other countries, not just India, but a lot of other countries. In fact, majority of the countries in the world, I guess, where there is no clear code about how repeatable things are across different markets in that country. And that makes it very hard because familiarity is lost, and it takes a lot more to train that model to operate successfully in those conditions. So that's the challenge. Now the opportunity basically here, which I tell everybody, especially from India, but everybody in general who asks me this question is, self-driving. India is a huge market, right? And again, look at Uber, Ola, and why they are going crazy about India. India is a huge market. These self-driving vehicles companies definitely would want to launch in India because that's where the money is as well. Like that's where the volume is, right? But what is preventing them from launching is this gap, this specific gap that you mentioned. Now, somehow imagine that, let's say there's a black box that you invent that is able to bridge that gap before they need to go design a solution in-house. You design that solution, and then you will basically enable them to enter the Indian market. And that's the opportunity that somehow, if you figure out a way to bridge the gap, they have the autonomous system, you don't have repeatability. You design a system that bridges that gap. That's where the opportunity is. That's probably multi-billion-dollar idea there.
Thank you so much, sir. I mean, this has been a really interesting session. I mean, I can see from the interest our audience is putting in and the number of questions coming in that everybody is very interested about this topic. But unfortunately, we are at the end of our session today, at the end of time. We could have done this all day and it would still be interesting, but we have to stop somewhere. So yeah, this is probably where we'll have to end this session.
Yeah, if anyone has any questions, you can send me over LinkedIn, Instagram. These are the two platforms I use a lot. I use Twitter a little bit as well, but feel free to follow me on these platforms, Instagram and LinkedIn, and feel free to send me questions as well. Happy to take a look and answer.
Yeah, and now I would like to
Sir, I want to ask, how do we start in this field?
Sorry, say that again.
Yeah, I'm sorry. Before that.
Okay, go ahead.
I would like to call upon Nirmalya Basu sir, who would like to speak something about this entire session. He is the head coordinator, student coordinator for NVCTI. So, sir, please.
Thank you, Anushka. And thank you, sir, Saiman, sir. It was really a very insightful session, and we were fortunate enough to have you with us. The students were also very much excited, being your such variant, such vibrant expertise in this field, and how AI is the burning topic, how AI is the new era, we can say. So it was really a great session, and you also have seen that the students were pouring with questions. So I think that was a very good end from our end and from your end, sir. And we hope we can have you further again with us with some sessions or with some workshops if possible, because that will be really helpful for the students and for our community altogether. Thank you, sir. And I would also like to thank Ria ma'am, who helped us with the coordination with you, sir. And to the end, I would like to thank all the audience, entire attendee, all the students who were present today for being there, for asking your questions. And it was really a good interactive session, I would like to say, if I may. So if you want to have such more further sessions, I will like the new students who have joined, the first year students, to go to our Instagram, Facebook, and all the pages, NVCTI, IIT ISM Dhanbad. You should go there, you should follow, and you will get endless number of such events we are organizing on every monthly basis. We are again having a session. We will be again launching another event. So you will understand how vibrant this session, this entire chapter, this entire organization is as well. So to sum it up, thank you again, Saiman sir. I hope we can have you again with us.
Thank you. It's been a pleasure.
Thank you, sir.
So I guess we'll be ending our session now. Thank you everyone for attending.